All right, y'all, today we're going to talk about even and odd functions. In class, what I had folks do was group up in pairs or 3 or 4 and work through problems 1 all the way through 8. Okay, so most of the ideas on questions 1 through 8 just deal with some algebra concepts using a table and a graph and talking about patterns. Okay, so I want you to try those, and I want to emphasize on questions like 3 and 4 and 7 and 8. I want you to just write in your own words what you're thinking. It doesn't have to be formal math language because we will add that on after the fact with our notes. Okay, so pause the video and try those 8 problems for me. Okay, I was looking for something like reflection over the y-axis for that one. There are really 2 types of symmetry, reflection symmetry and rotational symmetry. Okay, so you're most familiar with reflection. Okay, the note that I want you to add, because you don't have to write it like that necessarily, is our notation from kind of like our purple note card 1 through 4 steps. I'm going to use a lowercase r with the y-axis being the equation that I'm symmetric over. Now, the equation itself for the y-axis is x equals 0. And the reason I mention that is because we don't always have symmetry over the y-axis. Sometimes the line has been shifted over. Okay, so I'm going to get a little bit more in detail on that on number 4. Okay, so if we are talking about the table, there was some symmetry. Okay, on either side of the vertex, we saw the same value. Essentially, plugging in a positive x value and a negative x value are going to give you the same y value. Okay, something along those lines. Okay, and that's how one method it is to look at the functions equation and talk about whether we would see it. So we could use a table or just plug in a couple values, maybe 2 and -2, 3 and -3, and see if they give you the same y value. Another thing that we could talk about is transformations of graphs. Okay, so I said these could be shifted over. If you ever have a function that's given, this one was x squared minus 2, so that -2 translated it down. But if you ever have a function that's given in transformation notation where you could see that this has moved over to x equals 2 as our vertex, then we could say we have symmetry through x equals 2. So that means essentially for the equation, if it's in this formatting, and no h value for the case of specifically quadratics, because that's what we're looking at here, would mean that we have y-axis symmetry, because if there's no h value, it hasn't been shifted left and right, it's been shifted up and down. I do want to emphasize that does not apply when we have, instead of this transformation form where it's a and then x minus h in parentheses and a plus k. If instead we're looking at standard form where it looks like this, it's not as direct. Okay, and we'll talk about that dealing with one more thing that I want you to add here, and just add it between these questions 3 and 4 because it really is the math language for both of these. Okay, when we say subbing in x, we're talking about putting in x to an equation to find the y value. So we're going to talk about function notation. This really reads y, okay, but specifically it says the function's value, or the y, when you plug in x. So it's more specific. So we noticed that the y value when you plugged in positive 2 and negative 2 ended up being equal. So x represents one of those values, okay, and then negative x would represent the other. So plugging in opposite x values gives you the same y value. They are equal. Okay. The second part, you may not have noticed this as a rotation because, like I said, you're more familiar with reflections. Some people notice that this is a reflection over the x-axis and then the y-axis together, 2 different ones, and that's true. It's also a reflection over a slanted line, okay, but I want to refer you to these types of problems as a rotation instead. Okay, what I want you to add your note on this one as is a capital R for rotation. And this is specifically, I'm going to add it on this graph, and it may be helpful for you to do the same. The center of the rotation, because when we talk about reflections, it's over a line, but when we talk about rotations, it's around a point. The center of rotation is 0, 0 for this one, and this point has been rotated 180 degrees, half of a circle, around that origin. So you're going to put 180 degrees, kind of as subscript, and then you have to define the point that it cycles around, and that is 0, 0. Okay? Nothing wrong with you writing it out like a sentence if you want to, but you'll see me write it with the shorthand notation. Yeah, and this one, something like plugging in x and negative x give you opposite y values, or same number but different signs. Okay? In this case, if we talk about the function notation, okay, so write this with me. We're saying if you plug in negative x and you plug in positive x, doesn't matter really the order of these things, they're not equal like on the last one. Instead, they're opposites, and so we could say that we have a negative out front, because remember, this number in front when we talk about our scale change, like we did last time, refers to what happens with y, and that's what we're looking at, is our y values flip-flopping. Okay, just like I said, it doesn't matter what order you put these in when you write them. This negative could technically go over here as well, and it would mean the same thing. Okay, opposite x values go with opposite y values. Okay, so you can use an equation. You're not going to be able to see it with transformations of graphs, but we are going to talk about with this standard form, in this case it's a cubic, in this standard form of the polynomial, we can actually use this definition to find whether things are algebraically showing reflection over the y-axis or algebraically showing a 180 rotation. Okay, so here's the definitions that we just talked about. Okay, even algebraically means that when we plug in negative x, we get exactly the same thing as when we plug in regular x. Okay, even means equal. The algebra version for odd means when we plug in negative x, we get the opposite of what we do when we plug in regular x. So odd means opposite. But there's also the graph version. And the graph version of even, if you plug in opposite x values and get some y value here, and that same y value over here, that's reflection symmetry over the y-axis. Okay, graphically on odd says if I plug in x and negative x, I get some y value here, and this y value is going to be the opposite. Okay, so that's our rotational through the origin. Okay. There's one more version that you won't use a lot, but I want to tie it into what we talked about last time, and really what's going on with the graph here, the points specifically. So our scale change rule for even says if I plug in negative x, okay, so this is, or sorry, if I plug in x and I'm looking at it, and I do it under an even or a reflection, this point xy goes to negative xy. Okay, same thing here. This original xy, and I chose quadrant 1 just because they're positive there, but xy being positive x, positive y doesn't mean the actual values are positive. It's just easy to refer to them that way. And if we rotate it 180 degrees, now I'm going left and down, so that'd be negative x and negative y. Okay? Both of those switch. So I left this up here. This is on the back side of your sheet, but I wanted it up here on the same screen so that you could answer the next questions. Okay, it says classify our parent functions as even, odd, or neither by thinking about their graphs. Okay, so remember identity is another word for line. Think about the parent function of a line. Decide if it has even symmetry, which is reflection of the y-axis. Odd symmetry, which means 180 rotational, through the origin, or neither meaning something else. It could have no symmetry, or it could have a symmetry line that's not on the y-axis, or a symmetry point that is not on the origin, so something else. Okay? Greatest integer, remember, is your step function. And I'm going to have you pause the video and try to find where each of those go. You don't have to sketch it. I'll just have you list the name, but you will want to think about the sketch of the graph to figure out where it goes. Okay, pause the video and try that for me. Okay, here are the graphs. So identity, we have 180-degree symmetry. That's odd. You want to list it there. The parabola has symmetry through the y-axis. Okay, so that's even. This step function you may have struggled with. It kind of looks odd, because odd is to say you're seeing pieces of graph opposite corners from each other, and evens to say that they're next to each other side by side. But if I pick on this open dot here and rotate it 180 degrees, it would show up as that point, and that point is not on the graph. So this is a neither. Move it if you need to. Okay, cubic is 180 symmetry, so it's odd. Hyperbola or inverse is also odd for the same reason. This isn't a very good graph, sorry for my sketch, but the inverse square has the y-axis, so that's even. Square root does not have any symmetry at all, okay, so that's neither. Absolute value is through the middle here, and that is even. And this one also does not have symmetry, so it is neither. Now, none of our parent functions had symmetry. That made them neither. But there are some graphs that have symmetry, but that aren't even or odd. The example we've already talked about is y equals x minus 2 squared. This thing's symmetric, but because it's not symmetric specifically over the y-axis, it wouldn't be considered an even function. Okay, so we're going to practice the algebra version of finding whether equations are even, odd, neither without graphing them. Now, we may have to look at graphs when it comes to symmetry, but we're going to use the algebra definitions that we talked about on the front side for these. I want you to add them here so you don't have to look bad. Remember, odd means opposite. So when we plug in negative x, we get the opposite as when we plug in regular x. Even means equal, so when we plug in negative x, we get exactly the same thing as when we plug in regular x. And because both of these have us compare f of negative x to the original equation, that's what we're going to do. Directly below this, I want you to write f of negative x. This is a proof, which means all of these steps that I write are going to be required on your work to get full credit. But don't let proof scare you, because it's going to look very much the same every time, and you'll get pretty quick at it. Okay, here's what I mean by the same. We know we're going to sub in negative x. You're going to find where x shows up and just change it to negative x. In parentheses, because we've got exponents, and that's going to mean order of operations applies. Okay, so step 1 is just plug in negative x in parentheses. Okay, step 2 is we're going to simplify using those order of operations. If I take a negative to the 4th power, negative, 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 that's positive x to the 4th, and times that by 8, I can just smush them and call it 8x to the 4th. Same thing here, the negative squared first, that's positive x squared, times the negative 3 is negative 3x squared. So this is my f of negative x, the simplified better version, but I need to see both. Okay, what we're going to do is now go compare that to f of x, because that's what we want to know. Is that equal to the opposite of f of x, or exactly equal to f of x? So looking at the original terms, they match exactly. Here's how you'll write it. F of negative x, that's what we're looking at, and we're comparing it to the f of x. They were equal. Okay, that's our justification for saying that we have an even function. So you're going to say, therefore, that's the 3 dots in a triangle in math, even. Okay, so that's the proof of whether they're odd, even, or neither. And then we're going to state the symmetry. If we know it's odd or even, the symmetry is something that is always the same. We don't have to graph it to know. Even symmetry is always reflection over the y-axis. Okay, odd is always rotation 180 degrees through the origin, but neither we have to think about the graph to figure out. Okay, so let's look at this next one and see what happens with it. Same process, you're going to sub in negative x everywhere you see an x with parentheses. Okay, I can simplify this without writing out this step, but it is a proof, so this step is required. Okay, now we're going to simplify. A negative cubed is negative, so that'll be a negative 6x cubed. And then a negative 9 times a negative x is a positive 9x. We didn't have a power that we had to raise that to first. Okay? We are comparing this to the original, because that's what our rules do. And we want them to see if our terms are exactly equal or exactly opposite. If it's one of those things, it's even or odd. And if it's neither of those things, it's neither. Okay, so we started with 6x squared. This says negative, so it's looking opposite or odd. And then the second one started out negative and went to positive, so both terms are exactly opposite, so this one is odd. We'll write it as negative x, that's what this one was not the same as f of x, but it was the opposite, so that negative goes in front. Therefore, odd. And we just talked about all odds have some symmetry, 180 degrees around the origin. Okay. If you ever forget those symmetries, like which one goes with which, you can always graph them. Look at your graph and see which type of symmetry shows up. Okay. Do this next one. F of negative x equals 3 times negative x squared plus 5 times negative x. And the same process. Okay, simplifying negative squared is positive, times the 3, just tack it in the front. No power here, so negative x times positive 5 is minus 5x, and we're comparing that to the original. The first term is exactly equal, and the second term is exactly opposite. So this is our first example where we have a neither, and how we justify is actually the longest for this one. Those things that we just checked, we want to write out. So we always start with the f of negative x. But it wasn't equal to f of x. So we're going to put a not equal sign. But it also wasn't opposite all the way through. So we're going to say not equal to the opposite of f of x either. Therefore, it's a neither. Okay, but when we have a neither situation show up, what we want to do is think about the parent function. Okay, with the parent function, for this one, a squared means it's a parabola, and that means it is symmetric around this vertex. Okay, not necessarily the y-axis. In fact, we decided it wasn't since it's neither, but it's that vertex. So you have a couple options here. Okay, what I had them do first in class was just graph the equation, because that's going to be your default for any function that's a neither. If you're not sure what's going on, you can always graph it. Okay, so here we can look at 3x squared and then plus 5x. Okay, I'll zoom out here. Okay, and not really sure what this is going through. It looks kind of like -1, but we want to be precise. There's no guarantee that these aren't fractions, so we have to actually find that value. The vertex on your calculator is called a minimum or a maximum. In this case, it's a minimum. So you'll do second trace the minimum, and do a left bound on the left side of that vertex somewhere, and then do a right bound, right side of the vertex, and then enter to make it guess. Now we only care, because it's through the middle and it's a vertical line, we only care about the x value. And mine says -0.83 with a bunch of 3's, but then a random number at the end. And my random number is 5, but yours may be 2 or 4 or 6 or 1, something weird. It doesn't have to be the same, because when we're doing the left side and the right side, we have a little bit of error that could show up. Okay? And with that, we have to recognize when we see a lot of digits repeated in a row that our calculator is just messing up a little bit. So it's really that 8, 3 repeating. Okay, so if I get out of here, if I don't know what 8, 3 repeating is, I can put 0.83, bunch of them, and then just hit math, enter twice to change it to -5, 6. So it's still reflection symmetry, but my equation is x equals -5, 6. Okay, that's your backup plan. What I would like you to recognize is for quadratics only. This does not apply to all neithers. This is quadratics only. We always have reflection symmetry over opposite of b over 2a. Okay, hopefully that triggers a memory from Algebra 2. That's how we found the x value of the vertex. It's the front half of the quadratic formula. Okay, so opposite of b for us, -5. 2 times a for us is 6, and that's way faster than spending the time to graph it. But only if you know ahead of time that that is a parabola, a quadratic, and you know the rule. Okay, backup plan is go to your calculator. Okay, next one here, same concept, f of -x equals 0.5 times that -x to the 4th minus 2 -x squared plus 1, and we simplify. A 4th power goes positive times a positive 0.5. This one here goes positive, but we're multiplying by a -2. And then the plus 1 didn't have an x at all, so it just comes down. Okay, those ones, first term is equal, second term is equal, third term is equal, so we can say f of -x is exactly equal to f of x, and equal means even. Even symmetry, okay, if those are equal, left and right look the same, it's reflection over the y-axis. Okay, what I'm going to have you do now is work on problems 5, 6, 7, 8, those last 4 problems. Okay, there are some neithers symmetry that I'm going to come help you with, but I want you to pause the video and do those proofs for me. All right, so 5 was neither, but when you graph this in your calculator, because that's what you're going to do when you see a neither and it's not quadratic, okay, we're going to graph it to take a look at what type of shape it is. A 4th powers can look like parabolas, but sometimes they look like W's. Okay, you have to graph it to be able to tell which one is going on. And this one looks something like this when you graphed it. So if you were to try to draw a vertical line through the middle, because when we're seeing our arrows point the same way, both up or both down, if it's going to have symmetry, it's going to be a vertical line. Okay, but if you draw a vertical line through here, or where you think the middle is, it doesn't look exactly the same on the right and the left, which means there isn't symmetry. And there doesn't have to be. Okay, there is always symmetry for a line, for a quadratic, and we'll get to this in a second, but a cubic. But once your power gets 4 or higher, there does not have to be symmetry. Okay? This next one was strictly odd, so the symmetry is defined by our odd definition. Okay, nothing weird happening there. And then the last 2 were also neither situations. Okay, but these ones are cubic. So I'm going to graph this one, and I want you to do the same thing for this first one. Okay, so x cubed, and then minus x, and then plus 3. Okay, for this one, okay, symmetry is happening. We've got opposite directions, and in fact, I just mentioned cubics are always symmetric, so I want you to write that. And they're always rotation symmetry, so it's always 180 rotation. Okay, but if it's 0, 0, that means it's odd, and these ones were neithers, so it's not going through 0, 0 anymore. If you look for the middle, it looks like it might be 3, and that's really what you have to do on these ones is look to see. Because these points aren't minimums or maximums, your calculator doesn't have a feature for this, which is called an inflection point. Okay, since it can't find it, we're going to do our best to estimate it from the picture. Okay, you can use your zoom in feature and just go up to that where you think it might be at 3. Okay, noticing the constant, this +3 here that's going on. Okay, if you zoom in there, how you kind of check is you want to the right of this and to the left of this to look identical. If that's happening, that's where your point is. Okay? On the next one, if we do the same thing, okay, so now clear out your y equals and type in the next one. And I'm going to go back to a Zoom 6 window. Okay, and it looks like maybe it's 0, 1. Okay, again with our constant there. So I want you to zoom in and then go up to that 0, 1 so you can see better. Hit enter. Okay, to the left and to the right of this are not the same size. That means our middle point is actually a little bit over here to the left, which would make it go up some. And our calculator, like I said, cannot give us this. And in fact, you can't find it by hand without calculus. This is what it would actually be. Okay, but I'm not worried about that. What I'm going to have you do is just when it's not on that y-intercept, that constant, okay, just leave it blank. Say R180 because that's going to happen always with cubics, but you can leave it blank if it's not the constant. Okay, so now I'm going to talk about how we know ahead of time that it will or will not be the constant by looking at a pattern. Okay, so if we go back and look at all of our odd problems, okay, so we had a couple through here that were odd as we practiced through here. It was number 2 and number 6. Okay, and what I want you to do is pay attention to what shows up in both number 2 and number 6. Your powers were 5 and 3 here, and then they were 3 and 1 in those. Odd powers meant odd function. Okay, let's look if that same thing was true for even. So this one was even. 4 and 2 were our powers. That works out. Okay, this one was even powers, but we do have this constant involved. Okay, and then that was our only even. So the neithers were some sort of mixture, but we need to talk about constants for a second. Okay, we had number 4 that was completely even with a constant. Okay, if I go back to number 7, number 7, it was completely odd, but with a constant. When we think about a constant, it's like x to the 0 power. While 0 is neither odd or even, it acts even. So constants okay? And so when we look at our equation ahead of time, if for these cubics we have all odd except for the constant, this odd part is 180 through the origin, and this plus 3 makes it go up 3. But over here, this was not odd, which means it wasn't starting out at the origin, it was starting out at something else, and we can't find it without calculus. Okay? You are welcome on your homework to look ahead and see whether based on your powers you would have an odd, an even, or a neither function. But your instructions are going to say prove algebraically, and when it says prove, you have to show all the work. So I will not accept just seeing those pieces. I have to have all those parts that we did together to complete the proof. Okay? If you do have any questions while you work on your homework, please come in and see me.